Hopefully everybody else will show up, and we'll get to the system checks later on. So this is, make sure you're in the right room, integrating C++ and Python with Boost Python. My name is Austin Bingham. I work for and part own 60 North, a small software consulting and training and development company in Norway. So just a little bit about me, since you have me for 4 hours. I am originally from here, from Austin. I went to UT, and I love the picture of Stevie Ray Vaughan there, because that speaks a little bit to what the city's like. When I give talks like this in foreign countries, people get a kick out of that. Where I live now is across the Atlantic, up in Stavanger, Norway. We have different kinds of statues there. Those are the 3 swords commemorating the union of the Norwegian kingdoms under one king way back. That's about a 30-minute walk from my house. And then the bottom picture there is Lysefjord, the most beautiful fjord in the world. It's actually very stunning. If you ever go to Stavanger, this is what you will probably go to see, this kind of stuff. I've been there for about 5.5 years, but I love coming back to Austin. This is such a great city, even when it's 1,000,000 degrees like it is right now. I can't take the hot weather anymore. So, who in here? Any Norwegians in the room? Just to see. No. Okay. Folks from Austin. Okay. 1, 2. Okay. Good. All right. Right. So let's just kick into that. The first part of this talk is going to essentially be a lecture. I need to make sure that we have a sort of base level of knowledge about what is C++ Python integration, what are the kind of main moving parts, and so forth. Once we get past that, we'll get into actually doing code. So don't fall asleep on me in the first part, because it's important that we all have a common understanding. Hi, Björn. He's from Denmark. Give him a hard time. So, yeah, don't lose heart. There's going to be quite a bit of coding once we get past the initial laying of the groundwork here. This is available on one of the links on that Etherpad is to the IPython notebook. So these are slides derived from an IPython notebook, so you can get that and you can run it yourself. All this is available. And if you can't get it for some reason, just let me know. I'm happy to make sure everybody has access to this. You can get these, that's a good question. Does everybody have the student material for this course, all the exercises and stuff, the Git repo that I sent a link out to? Yeah, there was a link on that Etherpad. There's the Bitbucket is the link to, I believe, this presentation, and the GitHub has the GitHub repo has the student material. So there's one thing you have to have, and that's the student material, because that has all the exercises and stuff. I can't fix that. There's only so much I can do from up here. What we could do, if somebody wants to, I'm sorry, did you get something?
On your virtual machine, how can we get the command prompt to run the smoke test?
There should be, try pushing Alt F1 if you're on a Mac. Right. Access. Go to here. Sorry, yeah. There's only so many instructions I can give, but yeah. So if anybody has trouble getting to a prompt, let me know. We'll sort it out. But what we can try to do, if it's needed, is if somebody has the zip of the GitHub repository, we can put that on a USB key, and pass it around to folks who need it. Yep. Yes, there is a bunch of, a workshop. It's called SciPy 2014 workshop. Hold on, I can try to find it here. Okay. Does anybody remember that? It's 2014.etherpad.mozilla. There we go. Okay. Damn it. Did you get a prompt?
Yeah.
Okay.
If we have that thing, what the repository is that on
the virtual machine? The virtual machine has everything on it. That should be a fully self-contained working.
CD into the workshop exercises to make the plumbing test.
Yeah.
And it says that, there's no rule to make the target. Oh, never mind. Never mind. There's no rule for plumbing tests. This is your image. I mean, this is your image.
Yeah. I mean, plumbing test is there. Can't waste that long. We can just send a photo of that comment.
Has anybody else been able to get the virtual machine image working? And you make plumbing tests and it worked just fine? Mysteries upon mysteries. This is why these were supposed to be checked earlier. Okay, well, we'll get to that in a second. Here are the links to the student material. Here. And that's to the notebook, the iPad notebook. You don't need this. This is the most critical thing for the workshop. Right. Okay, we'll move on, and yeah, I'll see if I can help you guys in a bit here. So what is Python C++ integration? What do we mean by that? And by the way, raise your hand if at any point I'm losing you, because if you miss important parts of this early, then the rest of it makes no sense and has very little value. So if there's technical details that don't make sense, if I explain them poorly, or just for whatever reason don't land in your head right, just let me know and we'll try to sort that out. This presentation is ordered from most important to least important. So it's important that we get the early stuff. The later stuff, not so critical. And the early stuff is really conceptual in many ways. So still no dice. Yeah, getting all the pieces of this to fit together is a bit tricky, which is one of the reasons I want to lay the groundwork, because really just understanding the moving parts and what's involved in making Boost Python is that's 90% of the battle right there. So what is Python C++ integration? A lot of language integration, especially these days, and this is really the trend, is inter-process communication. Using things like HTTP JSON, that's a very popular, shared memory, Corba if you're really old school. But this is a really useful way to do language integration of all sorts, but it's not what we're talking about here today. What we're talking about here today is actually using CPython, the C implementation of Python, the standard implementation, as a library. That is fundamentally what the integration is we're talking about today. Was there a hand or? Sorry. Okay. This is in-process integration between the two languages, where code from Python land and code from C++ land are working in the same process at the same time. The key concept really, and this is what this picture is trying to show, is that almost all of Python, and I'm talking about CPython here, not to be confused with Jython or IronPython or any of the other implementations, is almost all of CPython is implemented as a C library. LibPython is typically what it's called. libpython.so, dynlib, whatever your platform's suffix happens to be. So we're talking about using that as a library in multiple different ways. Actually, we're going to focus on developing extensions today, and we'll bear down on what that means in a bit. So like I said, it's fundamentally just using libpython as a library. I'm going to walk away occasionally from here, so if I'm not talking loud enough, let me know. But there are two main ways to use libpython. Am I still on camera? Okay. Two main ways of using libpython, two sort of flavors. One is called extending, and this is where you've got Python the executable still running the show. He's running the main loop, so to speak, and doing things like garbage collection and so forth for you. And then that is using libpython, of course. That's most of the implementation of the language is. And then you write some module in C with the right face on it so that Python knows how to use it. The other way around is that you can actually have your program running with Python, driving the main loop, so to speak. This is where the Python executable is not in the picture anymore. You are taking its place and having to do all the work. Writing extensions is what we'll focus on today. I will touch very, very briefly. In fact, this is most of what I'll touch on in terms of embeddings. It's a more complicated topic and generally not as important for most scientific users in my experience. But if you have questions about that, catch up with me later and we can talk about it. It's something I know quite a bit about, and it's fun to talk about. It's very interesting. So, why would you want to write? Why would you want to write extensions? Because having to drive Python and having to deal with the low-level details of how the language is implemented can be very complicated. Well, it's great that you can do this stuff because it gives you a lot of power. It gives you a lot of fine-grained control over how the language behaves. You can bypass certain elements of the language, like the GIL, for example, and do very fast execution, like NumPy does. It's one of their tricks. It can help you with performance. This is a really good reason to want to, dip below the layer. And it provides interoperability with a broad base of existing software. This is really one of Python's superpowers. This is what gave it such a leg up, is that it could very easily integrate and pull in all these existing C libraries that let it do whatever you wanted to do. It was very easy and is very easy and straightforward to pull that kind of stuff in. But working with libpython is also very terrible because it opens up a lot of problems. The C API, Python's C API, can be really hard to work with. And we'll look at some examples and details of why that's the case and some of the pitfalls and common issues you'll face. You're responsible for doing things correctly. And what I mean by that is you're responsible for doing a lot of the reference counting that typically is done for you by the Python executable. This is a really common source of hard to debug problems, really deep, crazy seeming problems, because the reference counting is typically something you never think about in Python. But once you dip below into the CPython API, you're stuck doing it yourself, and you can screw it up very easily. This is the flip side of the same coin. It introduces all sorts of possibilities for new kinds of bugs, not just reference counting, but also you can manually deallocate things that you shouldn't be deallocating. You can be referencing into pointers that don't point to anything. All the kind of C kinds of bugs that you probably thought you'd never have to deal with again. So, are you sure you still want to do this? This is Virgil leading Dante into hell. I'm not sure which role I play here, but if you stay in the room, then you're going to see some of at least the dirty 9 levels of Python. Right, good. So everybody's staying. So the first thing we need to look at is the basics of the Python C API. I want you to have a sense of kind of how the API feels. It has a particular flavor, like most C APIs. Who here has any experience working directly with the C API? Some, so maybe 15, 20%, something like that. Okay, that's good. Then this will be a useful section. Kind of sitting at the core of this Python C API is this thing called PyObject. It's a big structure, and its size depends on how you've compiled Python, and this is also a source of problems. But we're not going to go into those details. But it is the central type for everything. And I wave my hands a bit here, but it's effectively true. It's the type of everything in the C API. Excuse me. Everything, sorry, I had a big lunch. Everything in Python is represented as a PyObject ultimately. And again, this is just this is the C implementation, not all of the other implementations. That includes things like strings, numbers, lists, modules, classes, functions, you name it. It's a PyObject under the hood in some way, shape, or form. PyObject is central for managing two really important, more than just two, but two really important things you need to keep in mind when dealing with PyObjects, is that a PyObject manages an object's type, so it knows the type of the thing it's pointing to. And this, if you ever call the type function in Python, what it's doing is looking at PyObject and asking it, what's the type thing you point to? And if you remember, everything, like I just said, everything in Python is a PyObject, and in fact, the type of a PyObject is itself another PyObject that gets interrogated by the runtime. The other trickier, scarier thing that PyObject manages is the reference count. So the reference count, I assume it's vaguely familiar, the concept is vaguely familiar to most people, but if I have a reference to a PyObject, its reference count is 1. Another reference count comes in, it goes up to 2. A reference drops, it goes back down to 1. The Python executable generally handles that for you. That's one of its big jobs. But if you use the Python C API, it's up to you to get that right. And if you do things like decref too many times, decrement the reference count too many times, Python will garbage collect things right out from underneath you, because that's how it knows when it can garbage collect things. So this is one of the real sticky points with the Python API, is this reference counting. And we'll talk in great detail about how to do it right and how Boost Python helps you. Actually, this is one of the things that Boost Python really is good at, is helping you manage the reference count. So, okay, the contrast is a bit bad here, but these are examples of PyObject in the C API. You see things like PyObject get adder. This is the function that anytime you say x dot something, it calls this. And you can see it takes a PyObject, another PyObject, returns a PyObject. I can explain what those are. PyEval get call stats. I don't care what the function does. What I want to show you is that it has a PyObject, returns a PyObject. And the same for PyAir set from something, something, something. All PyObjects everywhere. It's PyObjects all the way down. So it's pervasive universally throughout the API. So, okay, I scared you about reference counting, so let's look at reference counting in detail. Every object contains a reference count. It's just an integer that goes from hopefully just 0 up to something else. If it goes below 0, I'm not really sure what happens. The garbage collector, and I'll put that in quotes because some people take offense at calling what Python does garbage collection, but it is effectively garbage collection. Python uses this number to determine when it's allowed to delete something and take it out of the allocation pool, so to speak. When you decref something, when I say decref, I mean decrement the reference count, and incref is increment the reference count. When you decref something, it may or may not be automatically collected right then. It may wait until some unknown point in the future. But you have to assume that after you've decref something, it's gone and you shouldn't touch it anymore. As I mentioned, this is generally invisible to users of Python. If you go to the command line and type Python and start doing things, you never have to think about reference counting. And it may be a surprise to some of you that this is going on under the hood. But it's something you need to keep in mind if you ever do what I'm going to teach you how to do today. Here's some examples of reference counting, and I think it's better if I go over here since there's no shadows. Here I create a simple string, x, and I print out its reference count. There's a function in Python called getRefCount. So I can print it out. I create and if I do that, it says, okay, there's 3 references to it. 2 of those I didn't create. Those are part of IPython or somewhere in the Python file. But the important point is if I now say y equals x, that's another reference to the same object. Reference count goes up to 4. Great. And if I say now y equals none, basically telling y not to look at x anymore, the ref count of x goes back down to 3. Really simple concept, really easy, but everybody screws it up when they get down to this level. Here's an illustration of this same idea. I got x pointing to some string object with a reference count of 1. Y comes in and refers to the same object. Ref count goes to 2. Y points to none. The ref count goes back down to 1. This is also a good example if you've never really thought about how Python does reference semantics. This is pretty much how Python does everything. It has objects and it has names pointing to objects. So it's a good mental model to have if you start to get into advanced Python topics. Everything has a ref count. I talked about how everything's an object, so everything has a ref count. You can see here I've printed out the ref count of the none object. It is 11,896 in this case. You see the ref count of the sys module is 244 for some reason. Get ref count of the get ref count function is 5. So this gives you a really good sense of kind of how complete and pervasive and all-encompassing PyObject is in the Python world, the CPython world. I guess I keep hitting on this. Everybody understands that there are different implementations of Python, right? And we primarily use CPython, which is implemented in C. But there's all these other ones that actually don't have reference counting in them. So what I'm talking about here is very specific to CPython. I should make that clear. But I imagine, is anybody using anything but CPython on a regular basis? What are you using? SciPy. Okay, she's cooler than all of you now. So bear that in mind. I would love to use SciPy. It's just never quite the right time. So what can go wrong with reference counting? You can forget to increment a reference count. You can forget to decrement it. You can increment it too many times, and you can decrement it too many times. That is the sum total of what you can do wrong with reference counting. But it leads to so many problems. Because what happens is when you do things like decrement too soon, and Python collects objects from you, you start to get crashes in your C stack. and this happens in Python, it's really inscrutable. And even if you have a debugger attached, it's equally inscrutable because the crash happens sometime far after you've actually done the wrong thing. So you have to be very aware of reference counting. Again, I'm telling horror stories here, but by the time we start looking at Boost Python, you'll see how it actually solves this problem in a really graceful and useful and very intuitive way, actually. The reference counting API, because you'll probably run into this at some point, has macros like pyincref, pydecref, pyclear, so forth. And there's some links in this that if you download the notebook, you can actually follow the links, but it's in the Python C API documentation. You don't really have to know that stuff for now. I just wanted you to have a sense of what the API was like. Another interesting area that you need to understand or have some sense of how it works is how exceptions and error handling work in the C API, because this is something that when you start working across language boundaries, you have to manage that. You have to manage the fact that Python exceptions and C++ exceptions are very, very vastly different things, but they're conceptually in your brain very similar. But their implementations have to shake hands in some way, so I want you to have some sense of how the Python C API does things like signal errors and so forth. And we'll look at also how Boost Python makes this much easier in the future, or well, about half an hour. So C doesn't have exceptions, so obviously the Python C API can't be throwing any exceptions. So any exception thrown by Python has to be something that's implemented in C. There's no magic invention of exceptions in C on Python's part. So what this ultimately boils down to, in C Python's implementations, there are some global registers that get set. When an exception is thrown by some Python function, some variables, some global variables get set, saying what was thrown, what's its type, and what was the call stack. We'll look at that in a bit of detail. So that's how Python is emulating the notion of exceptions in C. So it's up to you. If you call any function in the Python C API, you have to check those registers after that call to see, did anything break? Make another call. Did anything break? Make another call. Did anything break? And it's really tedious, and as with all things tedious, you get it wrong a lot. So this is why, this is one of the big responsibilities you have to take on when you start working with the C API. So there are a number of ways with the Python C API to raise a Python function. The most common is this one, pyAirSetString, and I've actually never used anyone but this, and I've done a fair amount of this kind of work. Essentially, you give it a Python object pointing to the type of the exception, so an attribute error or an index error or something like that, and, a message. And that sets these variables for you, and then those variables can be interrogated after the fact by the caller, hopefully. The exception API can be quite tricky. Many of the C API functions clear the registers when they're called. It's the first thing they do. And this is because if they don't clear it, and an exception happened to have been set when that function was called, and then that function ends, it may look like they threw an exception when in fact they didn't. So many functions clear those registers. So if you have made a call to the C API, detected an exception occurred, and then make another call into the C API to maybe query those exceptions or something, you may find that these variables are getting, these registers as I call them, are getting cleared, pulled out from under you. And that's very confusing and very frustrating until you wrap your head around it. Some functions require the registers to be set, and the only warning you have that this is the case is the documentation. So you have to read the documentation and see, does it require that they be set? Typically, these functions are things like print the error, that kind of stuff. They require the exception to be set. If you really want to know how exceptions work and what the requirements of different calls are, you need to read the documentation. And this is a lesson to take to heart. If you use the C API directly, read the documentation in detail and make sure you understand all of the words and all of the doc strings that you read, because they all matter. Yeah, you laugh, but it's true. There's little code words in a lot of these that, unless you know what's going on, it will trip you up. Another key concept in the C API is this notion of protocols. And of course, there's a notion of protocols in the language itself, things that are list-like, things that are file-like. There's a whole set of different C APIs that mirror a lot of these notional protocols, things like the PySequence family of functions and the PyIter family of functions. So the PyIter family of functions work on anything that implements the iterable or iterator protocols, just like they do in Python. So there's mirrorings of the semantics in both languages. I'm not going to go into detail on this, but you need to be aware of it because it plays a role in understanding parts of Boost Python later on. So those are just a few examples. You can read all about this in all its gory detail on the web. It's all there. It's not great reading, but you should familiarize yourself with it a little bit. As you start working with the SciPy, if you ever have to do that, read the documentation. Don't blindly just start calling functions, because that's a recipe for immediate failure, almost guaranteed. So that's a really quick run through of the Python SciPy. Does anybody feel at all lost, confused, have any questions they want answered? Because I want to make sure that we are all solid as we move forward. All right, you all had big lunches. So let's do a quick sort of 30,000-mile, 30,000-foot flyover of Boost Python, then, some of the core concepts of Boost Python. A lot of what we're going to look at here is how Boost Python sits on top of the SciPy. I guess I should start by sort of just introducing Boost Python. So what is it? It's a C++ library. It's part of the Boost family of libraries. Has anybody used Boost? Any parts of Boost? Okay. Good. Okay, so Boost is the most world-class, best C++ library in the world, in many people's opinions. It's got a lot of great features in it. It's kind of the testing ground for new features of the language, actually. A lot of what was in sort of previous versions of Boost are now part of the C++ standard. It's a proving ground for the big boys in C++. Boost Python is just one library in this family of libraries, and what it does is make language interoperation between C++ and Python a little more seamless, actually a lot more seamless, a lot easier once you understand it. So C++ library talking to the Python SciPy, which is a C library. It's a way to make Python and C++ talk together. Okay, so we talked a lot about PyObject in the SciPy of Python. Boost Python's counterpart to all of this is these two guys, Boost Python Object and Boost Python Handle. We won't go into a great deal of detail about Handle, but it's essentially a smart pointer to PyObjects. It uses RAII, resource acquisition is initialization. Is that a concept people are, by and large, familiar with? I should ask this. Who's a C++ programmer? I mean, who considers themselves good at C++ on some level? Okay. Who's at least familiar with it? I mean, who knows what a destructor is? Because you're going to have trouble if you don't. Okay. I mean, you're not going to have trouble. I can get you using Boost Python, but I assumed a certain level of C++ knowledge for this workshop. So a handle's job is essentially to, when it's allocated, when it's constructed on a PyObject, it increments the ref count. And when it's destructed, it decrements the ref count. So it's a safe smart pointer. It's kind of like a shared pointer for PyObjects. It takes care of the hard work of remembering to decref. That's its raison d'etre. That's why it exists. Translating French on the fly. Boost Python Object is Boost Python's wrapper around PyObject. It presents a much nicer API, a much more idiomatically C++, yet still Pythonic API onto PyObject. One of the big things you notice when you use the SciPy, the Python SciPy, is that it feels nothing like Python. It feels like a completely alien 1970s era C library, because that's kind of what it is. It's not really 1970s, but it's old. It feels really old. Boost Python Object hides those details away from you and lets you work with an object as if you were still kind of in Python. It finds this great middle ground. So Boost Python Object, it manages a Boost Python handle, which is managing a Boost Python object. I don't know the exact rationale for why there's two things involved instead of just one, but that's the way it is. As I said, object and handle work together to do RAII or RIAA, depending on which acronym you like, to make reference counting much more foolproof. You can still screw things up because you can still get access to the underlying PyObject and fiddle with it all you want. So this doesn't, make you immune from screwing up, but it makes it much harder to screw up. This picture kind of gives you the main thing you need to know about Boost Python Object and Handle and how they kind of work together. So the idea is that when the object is constructed, really, I left Handle out because Handle just complicates the image. But the idea is when an object is constructed, it increments the reference count on a PyObject. When it's destructed, it decrements the reference count to the PyObject. And it has as a member variable this MPTR, which points to the Python object. So very simple relationship, pretty easy to understand. But you can see this is already a great step forward for having an API that's easier to not screw up, which is not a virtue of the SciPy. Here's a sort of basic example of how you would use Boost Python objects. This is our first code of the day. Here, we allocate a new list of size 10, I think that's what that parameter means, and assign it to PyObj pointer PyObj, construct a handle around PyObj and an object around the handle, and now you have an object managing the reference count for you. So what happens now if obj, that boost Python object, goes out of scope and destructs, it's going to decref PyObj, and then Python can take it back home. So let me go back up just a second here. This is talking about something called new references. This is one of these code words in the Python CAPI, new versus borrowed references. A new reference is a newly created Python object, or generally a newly created Python object that has been incremented for you. So you get a new list back from pylist_new. It's a new Python object, and it's been incremented to 1 or 2, probably just 1. The point is you don't have to increment it yourself. But PyObj will still decrement it because it knows it's basically been told you have ownership of this, you're responsible for decrementing it. There's another kind of reference. It's actually the exact same code and everything. It's called a borrowed reference. And a borrowed reference is one which has not had its ref count incremented for you. And this is typically found in APIs relating to, like in this case, list get item, where I say I want to get a reference to an item in a list. Python generally knows that you're not going to take that reference and then deallocate it immediately. So it says, I'm not going to increment this for you because that just takes time. It just gives it to you unincremented. So you have to tell Boost Python about that. You have to tell it to take a borrowed reference, so that it knows actually to increment and decrement so that you maintain the proper parity of inc and dec. Does that make sense? This is a concept I've never found a great way to explain.
Is that like a weak reference?
No, it's very different from weak references. It's really just a question of the distinction between new and borrowed is whether the object you've been given has been pre-incremented for you or not. A new object has been pre-incremented. A borrowed object has not been pre-incremented. And so it's the reason this matters to Boost Python is because it needs to know should it increment it, because it's always going to decrement it. Yeah, let that sink in. If you have questions, just ask me later or bring it up later. It'll make more sense, I think, as we go along. This is a bit of a fine point, but it's something you need to know about if you're calling CAPI functions directly. As I mentioned, Boost Python object presents a much nicer face on the PyObject concept. If I want to call a function using this, if I have a PyObject and I want to call a function on it using the Python CAPI, there's a function like PyObj get adder and then PyObj call or something like that. It's this long string of horrible looking functions. But if I have a Boost Python object, I can just call adder with the name of the attribute that I want to get, and it gives me back a Boost Python object, which was the result of resolving that reference name. So in this case, you can read this code as, I've got some Boost Python objects called obj, I'm sorry about the contrast again, constructed somehow, doesn't matter. And I want to call obj.food. I want to get that attribute. So that's what this is. That's really awful. Obj.adder food. This is why you need to download the slides yourself. This is get that. So adder, this is the same as obj.food. That's what this is like in Python code. And you'll see this over and over again. So adder is a really key function. It's a really key member function of Boost Python object because it's the way you do dot. It's essentially the dot operator. Objects are also callable. So the Boost Python object has operator parentheses. So it can be called with any number of arguments. This is great because this means that calling Boost Python objects is very natural. It's as natural as doing it in Python, except with just the necessary C++ syntax. What's problematic about this, and this is also problematic in Python, is that C++ doesn't actually know if the object you're calling is callable. At compile time, it can't stop you from trying to do things that are illegal. Not illegal, but will throw an exception. I mean, it's actually perfectly legitimate to try to call something, find out it doesn't work, and then move on. So with a Boost Python object, you can call it as if it were a function, as if it were a callable, with any number of arguments, and the compiler will always let that happen. And at runtime, you'll find out if actually that was a good thing or bad thing to do. Typically, of course, it's a perfectly fine thing to do, otherwise you wouldn't be doing it. Am I moving too fast? I have trouble telling sometimes, and I'm also very, very jet lagged. So okay, yeah, I flew in just the other day, so I'm still kind of in the middle of the ocean. So how do you create a Boost Python object instance? This is something you want to do in C++. You basically can construct objects with an arbitrary C++ object. So if I have a C++ object of it's an int or a string or a foo or a bar or a yak, it doesn't really matter. The compiler will always say great, because the Boost Python object constructor is templatized. So it takes any type of object and it always compiles. It doesn't always work, and there's a whole system involved in determining how to convert C++ objects into Python objects that can be managed by Boost Python objects, and we'll get into the details of that. But ultimately, what you need to know right now is that to construct a Boost Python object, you just construct it around any old C++ thing. This will always compile, but it may fail at runtime if there's not a registered converter. And registering converters is a significant topic. I have slides on it. I don't know if we'll get to them or not. We'll see how things go with the rest of the workshop. So it looks just like this. Here, like I said, I've created some objects of type foo. We don't know anything about foo. It doesn't matter. Nobody cares. Let me just say, Boost Python object obj called with f is foo. Boost Python will just do that. If it has a registered converter, if it knows how to convert foo into something that can be managed in Python, then this will actually work at runtime as well. Typically, if we replace foo with int or string or a number of other like basic data types like double and stuff in C++, that works out of the box. Boost Python has registered converters for all the basic types. And registering converters for your own types is, like I said, it's a bit of a challenge, a bit deep, but it's worth knowing about. So hopefully we'll at least touch on it later on, some of the details. Yes, type conversion, more detail later. Of course, you want to go the other way. Sometimes you have a Boost Python object that you've received from a call to Python somehow, or has been passed to you from Python, and you want to turn that back into a C++ object. So Boost Python has a type actually called extract, which is a templatized type, and you say extract with the template argument of the type you want to get out of the object, and then it tries to do that for you at runtime. Again, okay, when I say at runtime, I mean that all calls to extract will compile. So you can have code that's compiled and you think it works and it fails at runtime. This is just reflecting Python's dynamism. There's no way really around that. So how does that look? I have some Boost Python object, obj, and I want to get a foo out of it. I use the Boost Python extract call. It looks like a function call, but it's actually an object. In some cases, that's actually important. You have to create the extract object and then call it a certain way, but I won't get into the details of that because it's actually fairly rare that you have to worry about that. But this is an interesting example because this shows quite a bit of interesting stuff. So I've got an object from somewhere, again, it doesn't matter. I want to call the getFoo function on obj. So I say obj.adder, and the name of the adder I want is getFoo. So this here results in a new Boost Python object, which I then call, which results in another Boost Python object, which I then pass to the extract foo constructor, and then I assign to foo of f. What's going on in here is implicit conversion. So if you know enough C++, this makes some sense. If you don't, magic. This works. So is object construction and extract, does that make sense? I mean, it's just to Python from Python. That's what those two pipes are sort of for. So this brings us to exceptions. I mentioned that this is something that Boost Python simplifies for you a great deal. Reference counting and exceptions, two things that Boost Python really makes simple for you. So for the purposes of this workshop, we're going to talk about primarily, in fact exclusively, translating C++ exceptions into Python. So if you remember, I said we're going to talk about building extensions. So I've got Python's running the show. You're in Python land and you've called into some module that's written in C++, and that throws some C++ exception. And you'd like that to be translated into something meaningful in Python. So this is what we're going to talk about, how to translate, how to catch, deal with C++ exceptions, and turn them into something that Python can handle, a Python exception, that is. By default, Boost Python, when it detects an exception at the language boundary, so you've made a call from Python into C++, something horrible happened, an exception is thrown, Boost Python detects that all the time. They basically have a big catch around every call into Python. And they'll translate that into a runtime error by default. So no matter what you throw out of C++, they just say, catch ... raise runtime error with the almost useless message, unidentifiable C++ exception. That's really the best they can do. There's not really anything else that they could do without using something like boost exception, which people don't typically use. There are a few C++ exceptions which get default special handling, and this is relatively new. I didn't know about this until about a week ago, actually. But at this point in time, if bad alloc is thrown, you get a memory error. Out of range, you get index error, et cetera, et cetera. There's a handful of C++ exceptions from the standard library that get converted into standard Python exceptions, but by and large, they aren't. And anything that you develop yourself, any custom exceptions, you need to write your own handling for. And we'll look at how to do that. There is this thing called register exception translator, which we may get to the details of, but basically what it lets you do is say, if I see a C++ exception of this type, call this function. And that function can do something like raise a Python exception. That's typically what those do. So if we don't get to the details of register exception translator, just remember that it's there so that when you get to the point where you need to deal with it, you know to look for it. There's a way to do it, and it's the way, the proper way. You can read all about it in the exception translator documentation. Yeah, I've got a reference here to Boost 1410, which is actually pretty antiquated at this point, but everything that I'm mentioning here I think is still correct in Boost 155, which is the latest. You should be using the latest one if at all possible. Okay, well, translating Python exceptions into C++ is not really apropos to this talk, but we'll talk about it a little bit because it's actually, it's worth knowing about it. You could actually end up in loops there where it's important. So by default, Boost Python will translate Python exceptions. If its Python exception occurs and it propagates to the C++ level, Boost Python catches that also and converts it into a Boost Python error already set exception, which is a C++ exception. And all that's telling you is if you catch that in C++ land, it means that there's some extant Python exception. Whatever you called created a Python exception, and you need to go check those registers I talked about, the type, value, and traceback registers from Python C API. You can catch the error already set exception, and you can do whatever you need to do. Typically, that means translating it into some other kind of exception, but you can ignore it. You can call a handler function, whatever you want. But the key thing to remember is that all Python exceptions detected by Boost Python are turned into the exact same kind of exception, this error already set. And that's useful. A lot of debuggers let you set a catch on whenever some kind of exception is thrown, let me know kind of thing. So if you know that this is what's happening, you can always catch exceptions coming out of Python into C++. A really, really handy debugging tip, because some debuggers don't let you catch exceptions by type for some reason, is that error already set is only ever thrown from a function called throw error already set. So you can set breakpoint on that function. It's super, super handy if you start writing embedded code and things like that. It will save you, it'll save your mind and will save you hours and hours of time. Very good to know about. So at this point in the talk, the idea was to make sure everybody's system is ready to go. So who here, I know I asked this already, but who has been able to run the plumbing tests and smoke tests and is pretty sure their system works? Okay, it's not a huge number. Who thinks they're close? And just, okay. And who thinks they have no idea kind of what shape their system's in right now? Okay. How do people feel about like pairing up and things like that? That might be the way to go. If we can get in groups of 2 or 3 around machines that are ready to go, that might be the best thing to do. Because what I'm worried about is trying to get everybody's machine working and then finding out that it takes 3 hours to do that and we'll learn nothing. Do people feel like doing that? I mean, you're all cool with that? Okay, so people with working machines, raise your hand. Everybody else? If you want to follow along with the examples, find somebody to sit with.
I've got the virtual machine image also.
Okay. Is it on a stick or something? Okay, well that's something else we can do, is we'll get the machine image and we can try to install it on other machines for people with VMware or VirtualBox. We can try that route. Okay.